Okay, so last class we were starting to talk about percent composition, okay, and we were using an example of an ice cream sundae, and we had figured out what the formula weight of our ice cream sundae was, and oops, there we go. And then what we used that information to figure out what percentage of our ice cream sundae is ice cream, right? So we created the element symbol I for ice cream. Okay? And so I told you, try to see if you can figure out the percent composition for the cherry and the chocolate sauce. Okay, so so those are right here. Again, when we're trying to figure out the percent composition, okay, how much of a material is due to one thing, okay? We take the mass due to that one thing, so in this case the cherry, divide it by the total mass of the thing when it's all put together, and multiply it by 100%. Okay, so our ice cream sundae was 83% ice cream, 1% cherry, and 15% chocolate sauce, okay? And to check myself, okay, I took the percentages for the individual components that I determined, and they should add up to 100% the mass of the sundae, and in fact, they actually do. So I don't know why the second projector is not working today. It's Friday, it's probably real tired, but hopefully everybody can see well enough to see this projector. Okay, so we're going to do this with elements in molecules now, okay? And, oh, darn it. Let me see if I can quickly send myself the picture I took on Wednesday night that I said it's going to be so cool, I get to use this in class. So Wednesday night, I went to the American Chemical Society Binghamton section awards dinner. So it was at Binghamton University, and one of my research students was winning the award for Oneonta, and so they had this nice event. And they had a speaker there. And the speaker who was there, okay, had spent 25 years working for Corning Glass. He was a chemist who works for Corning. And so he gave, a talk about glass. And one of the things he was talking about, okay, was the composition of glass. Okay, so glass is made up of silicon and oxygen atoms, but there's a whole bunch of other things, okay, that you put in it to change, that you can change its properties. So, Pyrex glass, okay, is just the kind we use in lab, the kind you might use in your kitchen that can go in your glass baking dish. Okay, that has boron atoms in it, and the boron changes the structure of the material so that it can withstand rapid changes in temperature and not crack and break, okay? And so the fun thing about this talk is that, it's not going. Oh, wait. It is. All right, here we go. This is what I wanted to show you guys, is this picture right here, okay? So this guy who publishes in the Journal of Applied Physics, right, and who has spent decades as a chemist for Corning Glass, okay, spends a lot of his time figuring out exactly what the chemical composition of different glasses are and correlating it with its properties. So do they want to make a glass that can be used in a cell phone that folds? Do they want to make a really hard material that is bulletproof? And it all comes down to the chemical composition. So if you look, he put this up on the screen, and I'm like, oh my God, percent multiplication. We're doing that in class. How cool. So this isn't just an exercise in arithmetic to torture you. Okay, this is what actual chemists do to make the materials that are going to make the cool products that we use. Okay, so there's my little soapbox. So back to ice cream sundaes. All right, so actually we're leaving ice cream sundaes. So now, for this chapter, we're going to be kind of revisiting some of the early trauma of the semester with unit conversions, right? So the good news is that you've done a lot of this before, okay? We're going to be converting units between moles and number of atoms, atoms and moles, and the idea is we're starting to think about properties of materials and chemical reactions, and so we want to be able to take those things we can measure in the lab, okay, and turn them into this molecule has 5 atoms of this and 6 atoms of this, and they rearrange when it reacts with this other thing to have a compound that has 2 atoms of this and 4 atoms of that, okay? So we're going to kind of frame this in chemical terms now, moving away from the ice cream, okay? And we're going to talk about sodium in the diet, okay? So in my family, okay, high blood pressure is a thing. Low cholesterol is a thing. So good, don't have to take cholesterol medicine, have to take blood pressure medicine and avoid sodium, okay? Now, the FDA has a recommendation on how much sodium you should be eating, right, or you should consume. And that recommendation is 2.4 grams, or 2,400 milligrams, of sodium in a day. That's of sodium, okay? Now, if I'm trying to eat healthy and I'm cooking, all my own food from Whole Foods, the sodium in my diet is mostly going to come from added salt, okay? Salt, okay, is sodium chloride. So the amount of sodium chloride I eat versus the amount of sodium I eat are not the same thing, right? If I take 10 grams of sodium chloride, okay, that does not equal 10 grams of sodium, right? Some of that 10 grams of mass is due to the chlorine, okay? So we can figure out, okay, how much sodium is in 10 grams of sodium chloride, okay, if we know kind of the relative masses of sodium and chlorine. So remember, the masses of sodium and chlorine, okay, are different, okay? So we've got one atom, okay, sodium, that has a molar mass of around 22, and chlorine is about 35. So chlorine's a bigger atom. More of the mass, okay, comes from the chlorine than the sodium. So just kind of think of it in conceptual terms, not doing any math, okay? If I have 10 grams of sodium chloride, okay, less than half the mass is going to be due to the sodium, okay? So what we're going to do is we're going to be starting to use the relationships between the numbers of each atom type, okay, in compounds, and how much each atom type weighs, okay, to figure out, how much of a particular element is in a compound. And so if we go back to the glass example and we talk about percent composition, okay, as we're doing these percent composition things, okay, keep thinking about, what chemists are actually doing in the lab, okay? If we have a material and we don't know exactly what it is, we want to figure out what it is, we have ways of testing, how much of this element is there and how much of that element is there. And then, we can eventually get our way to coming to a chemical formula like NaCl for sodium chloride by knowing, first of all, how much mass of chlorine is there. Then, okay, our relationship between mass and numbers of chlorine atoms is the unit of the mole. Okay, and we have that, so we can turn our mass into number of chlorine atoms. We can do the same for the sodium, and then we can figure out what's the ratio of sodium atoms to chlorine atoms in this material, and figure out, the chemical composition of it. And then, armed with that knowledge, I can use that chemical to do other things and to, create new materials, participate in reactions that are going to be useful for us. All right, so again, this is reviewing things you already know, okay? So the molar mass, okay, is what's listed as the atomic weight, right, on the periodic table. So this is the molar mass, and it's units of grams per mole. And you had to use this a lot in lab this week, okay? And just a heads up, in case you haven't checked your email, I did a set of sample calculations for my lab section yesterday. I posted that document on Brightspace, but I also posted it for you guys in the resources section, and I made an announcement with a link to it. So if you're trying to do the calculations for this week's lab, you have that resource available to you. Okay, so the molar mass, okay, is the mass of 1 mole of atoms, of an element in grams per mole. Okay, so 1 mole equals that big ass number of atoms. Okay. All right. So again, it appears as atomic weight on the periodic table. So our favorite cheat sheet, the periodic table, tells us everything we want to know. All right. So also review converting between grams of a material, right, and the number of atoms we have, right? So if you're starting with the number of grams that you have and you want to know how many atoms. So let's say, okay, I have 16.2 grams of aluminum, okay, and I want to know how many aluminum atoms that is, okay? I cannot go directly from grams to number of atoms because I don't have a conversion factor that does that for me, okay? I do have a conversion factor that gives me grams to moles, and then I have another conversion factor that goes from moles to number of things, right? So for the first part of this, okay, if I want to know how many atoms that is, I would use the molar mass, okay? Pull out my calculator. Oops. Maybe I'm not going to pull out my calculator. Maybe I'll pull out the calculator on my phone. Nope, I had the calculator handy already. It's Friday. All right. So on the periodic table, okay, 1 mole of aluminum is 26.98 grams, okay? So I'm going to multiply by my molar mass. What's going to go on the top? First of all, what unit is going to go on the top? Moles, right? And so that means the grams is going to go on the bottom. What number is going to go on the top? 1. And then my 26.98 is going to go on the bottom. Okay. So this is going to tell me the number of moles of aluminum I have. So, 16.2 divided by 26.98. There we go. All right, and so that's 0.60 moles of aluminum. Okay. And so now if I want to know the number of atoms that I have, okay, I'm going to do a second conversion. Okay, and so for this, I'm going to use not Avocado's number, but Avogadro's number. Okay? But a little cartoon avocado is a lot cuter than Avogadro. If you've seen a picture of him, he's an ugly dude. All right. So we're going to multiply it by Avogadro's number. Okay? And so let's just talk about the units of Avogadro's number. It depends on, what your thing is. In this case, our unit is going to be atoms, right? So we're going to want to have moles on the bottom, the 1 mole on the bottom, and the 6.022 times 10 to the 23. Now, 1 mole is 6.022 times 10 to the 23 objects. In this case, our object is a mole, but sometimes, an atom. Sometimes our object is going to be a molecule. Okay, so it doesn't matter whether it's a molecule, an atom, a beach ball, an ice cream sundae. 1 mole of something is this number of objects. So we're going to call it atoms this time. Okay, so 6.022 times 10 to the 23rd. So we have 3.62 times 10 to the 23rd aluminum atoms. Okay. All right, so we did this kind of conversion at the beginning of the semester, and now we're going to use it in a useful way, again, to figure out what materials are made of. Okay. All right, so another sort of bit of review is if we have a compound, okay, if we have something that is made up of atoms of different elements, or I'm going to say elements because it can be something like O2, where we have the same element bonded together. Okay, so the compound molar mass is just going to be the mass of all of the parts put together, added together. So who here has ever been in a crowded elevator where you look at the weight limit and you look at the people around you and you do the mental math to see, like, should I get out of the elevator or not? That's like calculating molar mass, right? It's you're taking the weight of all the things, okay, and adding them together, and that's the mass of the thing, okay? All right, so your compound molar mass is just going to be the sum of all the atomic weights of the atoms in the molecule. So if we have something like SO2, okay, we have 1 atom of sulfur, right? And sulfur has a mass of 32.066 grams per mole. And then oxygen, we have how many atoms of oxygen? Well, I just wrote it up on the screen, so we have 2, correct? So oxygen is 15.9994 grams per mole times 2, okay? It's throw the calculator Friday. All right, 15.9994 times 2 gives me 31.9988 grams per mole of mass from the oxygen, okay? So my SO2 molar mass is going to be the sum of all of the atom masses that make it up. Okay, so it'll be 32.066 grams per mole plus 31.9988 grams per mole. 32.066. 64.0648 grams per mole. All right. Who here thinks chemists do this calculation all the time? Anybody? So, if we're working with a chemical in the lab and we need to make up a solution that has a certain amount of that material, okay, the first thing we're going to do is probably look on the bottle of the chemical to find out what the molar mass is. So this has a lot of different names. It can be molar mass, molecular weight, formula weight, lots of different aliases, okay? Also known as. All right, so we don't typically do this calculation all that much, unless we're trying to do what we call a back of the envelope kind of thing. But it's important, the concept that's important is that the mass of a compound is the sum of the masses of the atoms that make it up. Okay, so don't lose sight of the big picture here, okay? And don't be disappointed if the first thing you see a professor do when they're in the lab trying to work with a chemical is Google what the molar mass of something is, okay? All right. Okay, so we've figured out the molar mass of our SO2, okay, sulfur dioxide. So we're gonna, we've got the molar mass, and we can use it as a conversion factor, right? So we can also write this as 64.06 grams equals 1 mole, right? All right, so when we're going from moles to grams, okay, we have, in this example, 1.45 moles. And just a reminder that the unit mole is MOLE, but when we use it in calculations and in compound units that have more than one part, we just drop the E. It's not much of an abbreviation, but it's, it saves you one little loop, right? So 1.45 moles. Okay, so what's my conversion factor going to be? What's on top? 64.06 grams. And then my mole is on the bottom. Okay, so we got 1.45 times 64.06. So that winds up being 92.887. And that my units are going to be grams for that, right? Because if we, again, going all the way back to the beginning of the semester, when we did dimensional analysis, right, our goal is to cancel units to get the unit we want. And this is why I will nag about putting, every time you write a number, if it has units, put units on it, okay? With very few exceptions. All right, so now we're going to go in the other direction. So we've got 212 grams. All right, and so we're going to multiply it by a conversion factor. We're using the same information, how much SO2 weighs, okay, but in this case, we want to wind up with units of moles. So the mole's going to be on the top, and then the grams are going to be on the bottom. And remember that when we have a relationship between a unit and a number, they are married in a universe where there is no fault divorce. That unit and that number, they stay together. Okay, so you're never going to be putting the 64.06 with the mole. Okay, it's going to stick with the grams. Okay. All right. So our units will cancel. And what does our number come out to be? Oops. 64.06. See, oops. 0.0156. And that's in units of moles. Okay. So these are calculations that you've done before. Okay? They are calculations that you should practice enough that they are just non-challenging and non-daunting for you. And the only way to get there is to build your muscle memory, is just do lots and lots and lots of unit conversion calculations. Okay? All right. So now let's go back to our dietary guidelines for sodium and figure out how much table salt I can shake on my omelet in the morning and not exceed that amount, okay? All right, so the guidelines, okay, are less than 2.4 grams of sodium per day, okay? All right, oh, actually, we're making meatballs now. Okay, so my favorite meatball recipe, okay, calls for 1 tablespoon of kosher salt, which which I weighed, and it weighs about 5 grams. Okay, so we're going to call 1 tablespoon of the salt 5 grams, okay, per pound of ground beef. Okay, so how much of the amount of sodium would we consume if we ate 1/4 of the meatballs that were made? Okay, so how much salt is going to be in 1/4 of our meatballs? Okay, so if all the meatballs, 5 grams of salt. So I'm going to take only 1/4 of those. Okay, so I'm going to divide that. Oops. I'm going to divide that 5 grams by 4, okay? And that's how much salt I will consume. So that winds up being 1.25 grams of salt. And my salt, remember, is sodium chloride, okay? Is everybody with me there? Okay, so all the salt I put in is 5 grams. If I divided all those meatballs into 4 parts and I ate one of those parts, it would contain 1.25 grams of salt. Okay, so now let's figure out how many grams of sodium this is. Okay, so how many grams of sodium? All right, let me just peek ahead. Okay. I just wanted to peek ahead and make sure that I didn't have a slide that had everything written out on it before I wrote it all up. All right. So first of all, okay, we have to figure out how many, so our little map to how to do this, right, is going to be first, what is the molar mass of sodium chloride? Okay, so we need to know the molar mass of NaCl. Okay, so to do that, I'm going to add the masses of the 2 elements, because there's just 1 atom of each in my salt. So I've got 22.9898 grams per mole plus 35.4527 grams per mole. So 22.9898 plus 35.4527. All right, so that's 58.4 grams per mole. Okay? All right, so the second thing I'm going to do, okay, is if I'm trying to figure out, okay, how much of that 1.25 grams, okay, is salt, okay, I have to figure out how many moles of sodium chloride I have there, because I'm trying to treat it as objects, okay? So the second thing I'm going to do is how many moles of salt. Okay, so I've got 1.25 grams of salt. All right, so I want to convert to moles. What's going to be on the top? What's going to be on the bottom? So I want to wind up with units of moles, right? So what unit is going to be on the top? Mole. What number is going to be with it? 1. And then my 58.4 is going to be on the bottom. Okay? So we've got 1.25 divided by 58.4. So that gives us 0.021 moles. Okay? So I have that many moles of sodium chloride. Okay. Now, why did I convert to moles? Okay. because I want to be able to I want to be able to separate the amount of sodium, the mass from the sodium, from the mass from the chloride. Okay, and so figuring out these, I'm starting with mass. Okay, and if I put it into moles, I'm now in objects, so I know how many objects I have. Okay, and so now, next thing we're going to do is how many moles of sodium is there. Now, it is simpler in this case than it would be if we had a more complex compound, because if I have 1 mole of sodium chloride, okay, how many moles of sodium atoms do I have? So, well, let's do it this way. I'm going to draw out a picture for you. Okay, I'm going to say I have 1 dozen molecules of sodium chloride. 1, 2, 3. I'm going to be lazy. I'm going to copy. Copy, paste. Okay. All right. So there you go. That's a dozen molecules of sodium chloride. How many atoms of sodium are there?
So there would be 12. So
yep.
One mole would be 6.022 times 10 to the 23rd.
Right. So if we were talking about number of things, right? But we're going to stick with the unit of the mole. Okay. So if I have 12. So if I have So if I have 1 dozen NaCl molecules, I have 1 dozen sodium atoms. Okay? So if I have 1 mole of sodium chloride molecules, I have 1 mole of sodium atoms. Okay? All right. So now what we're going to do, okay, is we'll just do a kind of useless conversion, but just to prove the point, okay, what we're going to do is we're going to do, we're going to say we have 1 mole of sodium per 1 mole of sodium chloride, okay? And so that gives us, and I'm going to have to decrease the size of my handwriting. Let me see if it'll let me do it. I'm going to, no, all right. There we go. Hey, now I can make more stuff fit on the slide. Okay? And we'll zoom in so that you can see it. Okay. So that means I have 0.021 moles of sodium. Let me just get rid of my... All right. So again, in this case, I do this conversion and it doesn't change the number. But let's say I had water and I wanted to know how many, and I wanted to figure out if I have 1 mole of water, how many moles of hydrogen atoms I have. Well, for every 1 mole of water, I have 2 moles of hydrogen atoms because the formula is H2O, okay? So sometimes we need that step, so we're going to just practice by using that step. Okay, so remember our goal was to figure out how many grams of sodium were in those meatballs that I ate, right? So now I know how much a mole of sodium atoms weighs, okay? And I know how many moles I have. Okay, so my last step that I'm going to do is let me just make this a little smaller. So there we go. Okay, how many grams of sodium. So this is going to be a unit conversion. Okay, so to this point, I've done, addition and then several unit conversions. Okay, so we're going to go from 0.021 moles of sodium. And we know the molar mass of sodium, right, is 22.9898 grams per mole. So we want the moles to cancel. So those will be on the bottom. And the grams are going to be on top. So we've got 0.021 times 22.9898. So 0.482 grams of sodium, okay, is in those meatballs. So if we go back, look at that. All right. Could I have eaten the whole batch of meatballs? Let's see, 0.482 times 4. Yes, I could have eaten that whole pound of meatballs and still been under the FDA guidelines. All right. So, all right. So that's how we can use, again, our unit conversions to answer, questions that actually have some practical relevance. Right. All right. So now we're going to go back to our notion of the ice cream sundae and how much of the ice cream sundae was from each thing. But we're going to put it in terms of elements. Okay? And this is, we're going to be calculating percent composition, but what happens more frequently is you analyze things in the lab. Okay, so and you have, okay, I don't know my formula, but I can calculate how much of the mass is due to the carbon and how much of the mass is due to the oxygen, and then I put that all together and I can create a chemical formula for the material, okay? All right, so we have a sample of a compound with known mass, okay? So here it is. It's acetic acid, our old friend vinegar, okay? Can you tell that I like to cook and eat? Because all my examples have food. Later on, we'll have some medical examples, but I use mostly food. All right, so we've got a 2.5 mole sample of acetic acid, okay? We're given the formula weight, okay, and we want to know what are the amounts, okay, of each element present. And so those amounts, we can figure out how many moles, right? We can figure out in grams, okay? Or we could figure out percentage-wise, right? So, if I have 2.5 moles of acetic acid, how much carbon is in that sample? Okay, so let's look at it, okay? So, let's see the carbon, okay? So if we go to the periodic table and we look, okay, carbon has a molar mass of 12. Okay, so per 1 mole carbon. All right, so if we have, let's look at our sample of acetic acid. Whoops. I haven't figured out, sometimes when I put my hand down on this, it makes things go backwards and I don't know why. All right, so I have acetic acid. So we have 2.50 moles. Okay, so let's figure out in our compound, okay, how many moles of carbon are in 2.5 moles of acetic acid. So I've got 2.5 moles of that. So I have to figure out how many carbon atoms, okay, are in my compound. So how many carbon atoms are in 1 molecule of acetic acid? I've got 2, right? 1, 2. So 2 carbon atoms per 1 acetic acid molecule. Okay. All right, so that means if I have 2 atoms per 1 molecule, it means I have 2 moles of carbon per 1 mole of acetic acid. Are we good with that? Okay. 2 moles carbon per 1 mole acetic acid. All right? So we want to know moles of carbon. Okay, so this is, we have 2.5 moles of acetic acid. So we're going to use this relationship right here, and we're going to use it as is, right? Because we want to find out moles of carbon, so that's the unit we want to wind up with. All right, so we got 2.5 times 2. Well, duh, I can do that in my head, but probably not in front of a room full of people. All right, so I have 5.0 moles of carbon, okay? Now, let's think about how many grams of carbon that is, okay? How many grams of carbon is this? Okay. So, if we go 5 moles of carbon, and we've got our molar mass of what carbon weighs, right? So in this case, okay, I again want to find out grams. So, 1 mole of carbon is 12.0 grams of carbon. So 5 times 12 is 60 grams of carbon. Okay, so if I have 2.5 moles, I've got 60 grams of carbon. All right. So we can figure out, again, how many moles. We can figure out how many grams. So now let's figure out what percent of the mass of my compound is carbon. Okay? So that's our third thing we're going to do. Okay? All right, so what percent of acetic acid is carbon? So what we can do is we can take the number of carbon atoms in the molecule, right, and the amount of mass that we know those atoms represent. So let's say we've got 2 carbon, or let's assume we have 1 mole of stuff, okay, to make the numbers easy. So we've got 2 moles of carbon per 1 mole of acetic acid, right? All right. And we know what the mass of 1 mole of carbon is, right? And so we can figure out, hang on for a second. Do we have to do that step? Let me just think this through. Yes, we do. All right. So we get 12 grams of carbon per 1 mole of carbon. Okay. So my units here are going to cancel. Right? And this is going to tell me how many grams of carbon there are for 1 mole of acetic acid. Okay. So this is grams of carbon per mole of acetic acid. And I know what the total mass of acetic acid is, right? So the next thing I'm going to do, okay, is I'm going to use the molar mass of acetic acid, that formula right there, okay? And I'm going to find out what percentage of the mass of the molecule is due to the carbon. Okay, so in this case, we have 1 mole of acetic acid is 60.052 grams. Okay? So I'm going to have grams of acetic acid divided by, grams of carbon divided by grams of acetic acid. That gives us the fraction. And I'm just going to multiply it by 100% to figure out what percentage of that total mass of the molecule is due to the carbon. Okay? So we've got 2 times 12 divided by 60.052 times 100%. And so it turns out 39.97. So 40% of the mass of acetic acid is due to carbon, okay? Now again, chemists will typically do this in the reverse, right? What we'll do is we'll take a chemical and we'll analyze it and we'll figure out, okay, if I have 7 grams of, this chemical, and I test it to see how much oxygen is in it, okay, I can figure out what percentage of the mass was oxygen, okay? And then by doing kind of backtracking and doing these calculations in reverse, I can get to, okay, well, what is the molar ratio of elements in my compound? And that's how I get to these chemical formulas, okay? So, percent composition, and that's what we call percent composition. So when we talk about it, all right, it means the ratio of the atoms, okay, gives us the chemical formulas. So it's not the ratio of the masses, it's the ratio of the number of atoms. So we absolutely positively need our unit of the mole, okay? So it's not simply mass ratios, because our atoms are different sizes. Different elements are different weights. So we have to we have to put things on the comparing apples to apples, and the apples in this case is how many atoms are there, okay? Different masses. So we need to put things in terms of moles. Okay. All right. So the ratio of our masses, okay, gives us our percent composition, okay? But again, when I say we can't leave out the moles, that's what I mean, okay? So the calculation that we just did on the previous slide, okay, if we want to generalize it, it boils down to this formula right here, okay? You would take the number of the atoms in your formula, in your chemical formula, you'd multiply it by the molar mass of the element, divide it by the formula mass of the compound, and multiply by 100%. So we did that for acetic acid, and you can do that for any element in any compound you want. Okay? All right. So what I'd like you to do, in addition to working on the MindTap, is try to figure out the percent composition for N2O5, and these slides are posted on Brightspace. Okay, and again, we're always going to just assume we have 1 mole of the compound, and that that makes the calculations more straightforward. Right. All right. All right, and so that's where we'll start on Monday. Have a great weekend, and I will see you later.